So yesterday we made this model. We were just showing how the electrons themselves exist like this, okay, in a hybridized form. What we're doing today is taking and going forward from that and showing that when hydrogen shares this orbital, we talked about it sharing with the orbital up here in the orbital notation. When it shares this orbital, it somewhat elongates that orbital. And so instead of a round balloon, we get more of that hot dog shape. That's what you want to call it. We'll call it a hot dog shape. Okay? So this is the hydrogen over here. All right? And the same thing is going to happen with the other orbital that it's going to share. But the remaining two orbitals, they have the lone pair electrons in there. So these are our lone pair electrons here. These are the lone pair electrons here. Okay? And those orbitals are going to remain in that sort of shape.
Wait, why are those in the same shape?
Because we haven't bonded with them, haven't shared electrons with another atom, so they're going to maintain that shape.
Oh.
So this is the model you and your partner are going to make today.
Is that orange one the hot dog shape?
No, the orange one is this one right here. It's the unhybridized orbital. I mean, it's the hybridized orbital that's not bonded.
So that's a regular.
So this is where a lone pair goes. This lone pair right here.
And then the green and pink are the hot dogs?
The green and pink ones are the shared electrons. That's the kind of shape they form. Hello? So we made balloon models to show how water, starting with these sp3 hybrids on the oxygen, forming these sigma bonds with hydrogens, overlapping orbitals there to make those sigma bonds, form a molecule that still has a tetrahedral shape. Okay? Our unhybridized orbitals were tetrahedral. Now this molecule is actually a tetrahedral because the angles are roughly the same. They're not exactly the same, but close. But we have four arms, if you will, extending from the central atom in roughly, an equal spacing arrangement. Okay, that's a tetrahedral. Any bond, any sharing of an orbital, any sharing of electrons, where the electrons are shared in a space directly on a line between two nuclei, that bond is called sigma. That's a sigma bond. Anytime you share two electrons in a space directly on a line between two nuclei, that's a sigma bond. Okay, so it's sharing an orbital and sharing electrons. Same thing in this space. Okay? The lone pair of electrons in our Lewis dot formula up here, this lone pair and this lone pair, okay, they're in hybridized orbitals in a roughly balloon-shaped space around that central atom. So this balloon shape here contains the lone pairs on the oxygen in the water molecule. Okay? So when you label your balloons, not only should you label these as being sp3s, but you should also have on there your model that that's where the lone pairs are located. Okay? Each balloon represents the space in which you most often find those lone pairs. Each long balloon between the little ball at the end and the center, that represents the space where you most often find the two shared electrons between the oxygen and the hydrogen. Okay? So a shared orbital is a bond, is a covalent bond. Okay? But not all hybridizations of valence orbitals are the same. Carbon dioxide has both sp2 and sp hybridizations. So water was at least the oxygen in water, was hybridizing to sp3. We're now going to look at sp2 and sp hybridizations. Now, the reason we call this sp3 is because we went from our original unhybridized set of valence orbitals here. We had one s and 3 p's. If you hybridize one s and 3 p's, you get a set of sp3 hybrids. See where the name comes from? Really complex, right? One s and 3 p's makes an sp3. Okay. One s orbital and 3p orbitals being hybridized into the same kind of orbital, sp3s. Okay? So sp2s means that we're hybridizing 1s and 2p's, and sp means we're hybridizing 1s and 1p orbital. Okay? So carbon dioxide is CO2. We've already done the Lewis dot formula for that. We have carbon. Well, let me make this an oxygen on this end here. Give myself a little more space. Oxygen, carbon, oxygen. We shared 2 sets of electrons between the carbon and the oxygen, making a double bond in between. And then each oxygen had us 2 pairs, or 2 lone pairs out here. Now each of the oxygens then is going to go through what is called sp2 hybridization. That means we're going to hybridize 1s and 2p's, and if we start out with an s and 3p's, what we're going to do is leave for oxygen we're going to leave 2p, for oxygen we're going to leave 1p orbital unhybridized. Okay? To have an sp2, we've got to hybridize 1s and 2p's, so one of the p orbitals is left unhybridized. So here's oxygen. And I'm going to leave this pz orbital here unhybridized. So I'm going to redraw the pz orbital. Remember, it's double balloon when it's the unhybridized original p orbitals were just double balloon shapes. pz. Alright, so in our original sp3s, we hybridized all 4 of those orbitals here, making 4 equal shape, equal energy sets of orbitals. We're going to hybridize only 3 of those this time. Okay? The result then is that I'm going to have 1 orbital that I'm hybridizing going in this direction. I'm going to have another orbital coming kind of out toward you. And the final set of orbital in this set is going to be kind of in behind here. Okay? So these are sp2 hybrid orbitals. What? pz. Yeah. pz. Yeah, as in zebra. Yeah, there you go. As in Z. Z. So this is an sp2. 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 The carbon, on the other hand, goes through sp hybridization. So sp means they want to hybridize only 1s and 1p. That leaves 2p orbitals that are unhybridized. Okay? To get sp hybridization, I hybridize an s and a p, but I leave 2 of the p orbitals unhybridized. Okay? So here's our carbon nucleus right here. I'm going to leave, let's leave one of the pz unhybridized here on this one as well. Okay. pz. Leave pz unhybridized. Let's also leave py unhybridized. I'm going to make that a blue one here. So we've got to leave 2 p orbitals unhybridized So we've got a PZ and a PY we're going to leave unhybridized. Okay? We're going to hybridize one s orbital, and that's a hybrid orbital is a single balloon shape. Okay? So this is going to be an SP, because I'm going to hybridize only two orbitals. And the remaining orbital, I guess, is going to be orange. And that's also an SP. Now, here's what happens. These two orbitals join up together and form a single orbital between the carbons. Oxygen, carbon, and we're going to get that sigma bond shape here. So there's a sigma bond. Okay? The PZs, notice they're parallel to each other. You see how the PZs are parallel to each other? They're both running up and down. Like the old AT&T commercial, they're going to reach out and touch each other. So what we're going to have here is a shared orbital that has space above and below. This is called a pi bond. Both these nodes are part of the same pi bond. The Sp2 that has a lone pair of electrons in it. That's not going to be that's not going to do anything but stay there. This Sp2 has nothing but a lone pair of electrons. It's going to stay there like that.
What is that little symbol inside the sigma?
Here,
Inside the sigma.
here, this is sigma, and this one is pi. So this is Sp2, this is Sp2. Okay. Now the other oxygens on the opposite side over here, there is also a sigma bond here. Okay. And there's going to be another pi bond over here, but it's going to be a little harder to figure out. And I'm going to wait till you finish your balloon models to show it to you. Okay. Now, the reason they form these kind of bonds, two electrons can occupy the same orbital only because they become quantum entangled. They have opposite spins. So, four electrons can't occupy the same space. I got four electrons between the carbon and the oxygen. So I have to have one orbital here and another orbital top and bottom like this, so that they're not occupying the same space. Okay? Got that much? Alright, so we're talking about VSEPR, valence shell electron pair repulsion. Keyword, repulsion. The electron repulsion. Got it? Alright, so here's what you're going to do for your next model. We're going to start with the pi bond. Take a long balloon without any air in it and tie a knot about an inch from the end. Long balloon, about a knot about an inch from the end. After you tie a knot about an inch from the end, you want to blow up another wiener. Only this one's not going to be 9 inches, it's going to be 15 inches. About from your little finger here, to your elbow, for most girls anyway. Okay? Little finger to elbow is about 15 inches. Alright?